Well, I found out that the other video that I did went blank right around this point. So I thought I would back up a little bit and show you where we were at when the video kind of went just to audio. And so I guess I had presented this set of steps for how you figure out what orbitals are involved in the bonding in simple molecules. And it starts with the Lewis structure. And we have already got the Lewis structure here from before. And I guess I circled some of these, so it's not so clear, but I'll redraw it. So we just have single bonds from the carbons to the hydrogens and a double bond between the two carbons. And what that tells you, so if you look at step B here, it says figure out the number of groups of electrons on the central atom. And you see that there are 3 groups of electrons. Remember that a double bond counts as 1 group, 2 groups, 3 groups. And this second carbon also has 1 group, 2 groups, 3 groups. So it's 3 groups of electrons on each carbon. That is equal to the number of equivalent hybrids. So once you know this number, it equals the number of equivalent hybrids. That's pretty much always true. So it's an important thing to know. Okay, the next thing we're going to do is to draw the energy diagram, which actually I already did, and that's on the previous video. So if you remember, this is for each carbon. So this is for carbon number 1, but it's the same for carbon number 2. And, carbon is 1s2, 2s2, 2p2. So here's 2 in the 1s, 2 in the 2s, 2 in the 2p. And unfortunately, we need half-filled orbitals to do overlaps. So what we do with carbon is we promote an electron. We basically excite a 2s electron to the 2p so that we have 4 half-filled orbitals. And because we know we need 3 equivalent hybrids, we circle the 2s and 2 of the 2p's. That's 3 total orbitals, each being 2 parts p and 1 part s. And we use our orbital arithmetic, 1 2s and 3 and 2 2p's. Did I say 3? I shouldn't have. That's 1 plus 2 equals 3 sp2 hybrids. So here we're circling one of the 2 s's, 2 of the 2 p's, and we make 3 sp2 hybrids, and we have 1 p orbital here. That's going to be for the double bond, for the second bond of the double bond. So let me go to the other OneNote page, and here we are. So here we have the Lewis structure of the C2H4, and I have both the carbons listed here. So in other words, I copied the exact same energy diagram that I just showed you that has 3 half-filled sp squared hybrid orbitals and 1 half-filled 2p on each carbon. Okay, now let's figure out what orbitals overlap to form bonds. Okay, so when you look at this structure here, you see that each carbon has a bond to hydrogen, has 2 different bonds to hydrogen, right? So each hydrogen has a bond to carbon, but each carbon, of course, since there's 2 hydrogens. So if we talk about the sp3 hybrids that we have, sp2 hybrids, excuse me, on this carbon, so we have basically these 3 things sticking out. 2 of them are going to overlap with hydrogen 1s orbital. So 2 of this one here, let's not circle this one right now. So the 2 that I've circled here, these are sp2 hybrids on the carbon, and they will overlap with 1s orbitals on each hydrogen. So each of these overlaps with 1 hydrogen, 1s. So you will have a sigma sp squared, 1s, and a sigma sp squared, 1s. Why is it sigma? Because here's the hydrogen nucleus, here's the carbon nucleus. This is the internuclear axis, and the overlap is on that axis. Same thing over here. Here's the nucleus of the hydrogen, somewhere like that. We draw a line. That's the internuclear axis for that bond. And the overlap is right here along that internuclear axis. And of course, it's the same on this side. So here on the other side, we will have a similar situation where this one, or pick any two of these, it doesn't matter which you pick, each overlaps with a 1s on hydrogen to form a sigma bond from sp squared on carbon to the hydrogen 1s. Okay, so we've sort of taken care of these two orbitals. Now, the remaining one, I guess I could say that these two for that, and the remaining one here. Okay, this will be, let me get rid of this, and the third sp squared. Okay, I didn't do a very good job there, but something like that. These are the hydrogen overlaps. Guess I should have done a better job there. Okay, so this is overlap of an sp squared on each carbon. So this is a sigma bond, because again, here's your internuclear axis. And the overlap is on that axis. Okay. And let's not forget the angles here, okay? Because remember, this is a trigonal planar structure at each carbon. So this is, all these angles are 120 degrees. And this is a flat molecule. It's all in the plane. So here's a plane, flat surface, and you've got your sigma bonding here in the plane. And then now we have these leftover 2p orbitals, and these come together and overlap. So they're sticking out of the plane. I'm exaggerating it. Here you go. And this overlap is a pi bond. And notice that the internuclear axis is down here. It's down here. Not working. Let's see. Here's the internuclear axis. And the overlap is above and below. The overlap is above and below the internuclear axis. So it's a pi bond. And what's true is whenever you have a double bond, the first one will be a sigma, the second one will be a pi, always from overlap of 2p orbitals. And notice this is not two bonds here. These two overlap regions, this is one pi bond. There are just two electrons. Okay. A lot of times, like I said, you could draw the p orbital overlap to be like this. But when you do that, it's so close together that it's hard to draw the rest of the molecule. So we tend to draw it like what I showed here. So the whole thing all together, well, let me just show you the nice pictures, okay? So this is what I call a top view. If you're looking down on that plane from the top, you could see, and these are very prettified, right? They're much better than what I could draw. These three sp2 orbitals on each carbon. Here you see them overlapping. That's the sigma sp2, sp2. And these are the 4 overlaps, right? All of these are sigma sp2 1s, okay? But now we're looking down on this. So where are the leftover 2p orbitals? They are sticking out. It's kind of coming towards us and going back behind the tablet. Okay, so if you take this picture and you tilt the diagram, so now you're looking, instead of looking at it flat, you kind of look at it from the side, and these guys here are now coming out towards you. Okay, and so these are the ones that are coming towards you. These are the ones that SP. So then these other ones would be look like they're going back. These are coming forward. And you tilt it. And now you can see that where the 2Ps are. And they draw it like this just to emphasize the overlap. But it's like as if you had a 2P here and a 2P here, and this is the overlap. But they draw it in this way that shows the mushiness of the electron clouds and stuff. And again, these are your 2p overlaps. These are your basically your 4 2 bonds to hydrogen on each side. So this overlap here is a sigma sp2 1s, as is this sigma sp2 1s, and the same thing on the other side. These are all sigma sp2 1s, sigma sp2 1s. Okay, so now where are we on our instructions? I don't even think I have the instructions here, but I'll go back to the other one and look. So we had this long set of instructions. So figure out the number of groups that equals, we did that. Draw the energy diagram, we did that. Figure out which orbitals overlap to form bonds, we did that. And then it says to draw the molecule showing orbital overlaps. And we did that as well. So we've basically done everything. I guess if we drew them with all the overlaps, we'd have to do, let me just show you, we'd do this, this, this. Here's your carbon, your 2 carbons, each with an each with 3 sp2 hybrids overlapping the hydrogens. And then sticking out of the plane, you have the 2p's, which I didn't draw very evenly, but who cares? Right. And so that's all of the bonding. These are all sigma sp2 1s here to the hydrogens. This is the same, 2 sigma sp2 1s bonds. Then we have this one in here. Try to color coordinate it. This is the sigma sp2 sp2. So this is the first bond of the double bond. And this guy here is pi 2p 2p. This is the second bond of the double bond. And finally, and this is what you really should know how to do. If we draw the molecule nice and big, you should be able to label the bonds with what the overlaps are. So these again are sigma sp2 1s, sigma sp2 1s, as I've said before. So are these. One of these is a sigma sp2 sp2, and then we have the pi from the overlap of those leftover 2p orbitals. That's kind of the end of that example. All right. Okay, so I want to move on to the next problem. Yeah, I showed you that already. Okay, so I want to do the CH2NH example that I did in class, but it didn't record. And it starts with drawing the Lewis structure, which of course starts with counting the electrons. So here we have, from from the 2 hydrogens. Actually, there are 3 hydrogens, so that's 3 electrons. And then we have the nitrogen is 5 valence electrons, and the carbon is 4. So that's 12 electrons, or 6 pairs. So we start with single bonds, 4, and then we use lone pairs. That was 4. So now we have 5, 6. Right. And we don't have an octet on the nitrogen. So we're going to take this lone pair. And this is our Lewis structure. But is it drawn with the right geometry? You know, the answer really to that is no. Because we know when we have 3 groups of electrons like we have here, okay, we know that's going to be a trigonal planar arrangement. So we're going to have 120-degree angles. Okay, and then we'll have a lone pair going in that direction. So this is all 120-degree angles. This angle is a little bit less than 120. Why? Because the lone pair kind of squeezes down on the other bonds because it takes up more room. But all of these are going to be 120 degrees. And we kind of already did some of this stuff just now. So how many groups of electrons are on the carbon? There's 3. What hybrid orbitals will form? You'll get 3 hybrids. Since you always have 1 that's S, you'll have to have 2 that are P. So it's going to be S1, P2. We call that SP squared. So we're going to have 3 SP squared hybrids. And now we can draw for carbon anyway, which is 1s2, 2s2, 2p2. So we put in our electrons. And then we do what we always do with carbon, which is we promote an electron. Like that. So we still have 1s. We still have 2s. We still have 2p. But now we have 4 half-filled orbitals. That's still not what we need, because like I said, we need these sp2 hybrids, and there are 3 of them. So we're going to circle the s and 2 of the p's, and we're going to hybridize these. And then again, we have 1s, but now we go sort of part way in between the energy of the 2s and the 2p. And here is our sp2 hybrids. And then we have 1 leftover p orbital there. Okay, so these are all half filled. Okay, so this is what we have for carbon. These are ready for bonding. They're half-filled orbitals. Now let's look at nitrogen. How many groups of electrons on nitrogen? Well, we have 1, 2, 3. Double bond counts as 1. So that's 3. So again, we'll have sp2 hybrids. But it's only for carbon that you need to do that promoting electron business. For nitrogen, you don't have to do that. And nitrogen's configuration is 1s2, 2s2, 2p3. So we have 3 half-filled orbitals. But again, we need to hybridize. So we're going to use, since we want sp2 hybrids, we're going to pick 1s and 2 p's. We'll make 3 sp2 hybrids. We have a leftover 2p orbital. Now we have a lone pair in one of those, which isn't surprising, because if you go back and you look at the Lewis structure over here, you notice that there's a lone pair. And that lone pair is going to be in an sp squared hybrid. So that's not terribly surprising at all. Okay, so we've already done this. What is the HCH bond angle? So if this is our Lewis structure. We've already talked about how these angles are all 120 degrees. I know that because it's trigonal planar. And it has with 3 bonds to atoms. No lone pairs. So it's exactly 120. What is this bond angle? So we're talking about this one, this angle here. Well, because of the lone pair, which takes up a little bit more room, this is going to be less than approximately 120. Oh, I should have written that above. How do I know it? Is because it's also trigonal planar geometry with 1 lone pair, so the angle is a bit smaller. Okay, and now we're going to figure out how these orbit, so we have this for nitrogen, we have this for carbon, and now we're going to put them together. So I'm just going to redraw them here. So for carbon, and I don't care about the 1s squared, just leave it out because it's not involved in the bonding. We have 3 sp2 hybrids, and then we have a 2p orbital. I should write this over here. And then for nitrogen, we also have 3 sp2 hybrids, and we have a 2p orbital over there. Now, if we think about where the electrons are for the carbon, they're all half filled. Okay, so I'm just going to put 1 electron in each of these. For the nitrogen, we have a lone pair in one of them, don't forget. And the other 2 are single, and then we have an electron in the 2p. So what are these overlaps going to be? Well, notice, because again, we have this Lewis structure, that 2 of these sp2s will overlap with hydrogen 1s orbitals. So we will have sigma, so there'll be 2 sigma sp2 1s's for that. For nitrogen, there's only 1 bond to hydrogen, so we will have this overlapping with a 1s on hydrogen. So we'll have a sigma sp2 1s there. Okay, but now we have this guy and this guy. Okay, and that is an sp2 overlap. So that's between the 2 carbons. I should be drawing this actually, yeah. So we have our carbon and our nitrogen. And so we've already used here's 2 of the sp2 hybrids, and they overlap with hydrogen 1s. Those are the 2 I did here. Okay. Then we have the last one, which overlaps with an sp2 on the nitrogen. And so this is a sigma bond between the 2 sp2 hybrids. Then we have a lone pair in the sp2, in an sp2. And then finally, the third one overlaps with a hydrogen 1s. So this is sigma sp2 1s, as are these 2. And again, the overlap region here is along the internuclear axis for all of the ones I've done so far. So they're all sigma bonds. All right. And like in the other case, the other molecule we just did, I don't know if I did this on the tape, but anyway, I'm doing it again, so that's fine. We have these two p orbitals that are sticking above and below the plane of the molecule. So again, most of this molecule is in is in a plane. We have a lone pair and a hydrogen and two hydrogens. And then we have these two P's sticking out, these leftover P's. So this one and this one that come together and form a pi bond between the two P's because they overlap above and below the plane. The internuclear axis is nowhere near where that overlap is happening. The overlap is above and below the plane of the molecule. So just going over our bonds again. Okay, we had mostly sigma bonds. We just had one pi bond. That was between the carbon and the nitrogen. We had two of these were sigma sp2 1s between carbon and hydrogen. That is this overlap and that bond and that bond, the two checked ones. Then we have sigma sp2 1s between the nitrogen and the hydrogen. That's this bond. And finally, we have the first bond of the double bond, which is sigma sp2 sp2. No, I guess I labeled it already on top. There it is. Okay. And then we had a lone pair in the sp2 on the nitrogen. That's this guy over here. Okay. Now, finally, we like to draw this, a large version of this, and label the overlaps and label the bonds. Sigma sp2 1s, sigma sp2 1s, sigma sp2 1s, sigma sp2 1s, and finally pi 2p 2p and a lone pair on the sp2. Now, really, you don't have to go through all the stuff we did there with the energy diagram to come up with something like this. What you basically need to do is to be able to look at this carbon and see that it has three groups, which means you have sp2 hybrids. You look at this nitrogen, you see it has three groups of electrons. So that means you'll have sp2 hybrids. So it's really not quite such a mystery. You could have gone directly to labeling the bonds because there's no ambiguity at all about the orbital that you overlap with on hydrogen. It has to be a 1s. And you always know that the pi, the second bond of a double bond, is 2p, 2p. Now, I did start the next example, which was acetylene, C, triple bond, C, H, H. So it's C2H2. Okay, I didn't get very far though. But I did start to talk about the fact that you have two groups of electrons. So a triple bond is one group also. And so you have two groups of electrons. That's a linear molecular geometry, also electron geometry. And so you will be forming two equivalent hybrids. And what we do is we combine one 2s and one 2p to get two sp hybrids. What happens is that the s orbital combines with the p orbital, and you get sp hybrids that point. So this would be one sp hybrid going this way, and another one going this way, another. And I want to point out that each of these is an sp hybrid. This is not showing a p orbital. The hybrids, like I said, they're sort of they're in between s and p. And it's funny when these books, they show like an sp squared hybrid, sp cubed hybrid is looking like this, an sp squared hybrid is looking like this, an sp hybrid is looking like this, but really it's not quite the way it is. The sp3 hybrids are more elongated. They get squatter as they get to have less p and more s character. sp3, sp2, sp. Notice the more s there is, the fatter the orbital is. This is more elongated. Anyway, this is where the movie ended, so I'm done. I'll have to start here next time. Okay.